Hello and welcome to Engineering Ethics at NJIT. I'm your instructor Daniel Estrada, and this is the lecture video for Lesson 12, What is Artificial Intelligence? We're starting a new unit of the course. Lessons 12, 13, and 14 will all be dedicated to artificial intelligence and various ethical questions that it raises. Artificial intelligence and ethics is a primary research area of mine. I also teach a class at NJIT HSS 405 on artificial intelligence and the problem of autonomy. So if this is an interest of yours, you might think about taking my 405 class. We're going to be spending the next few weeks in this class on this topic. That's how much I like it. Lesson 13 will be on the question of autonomy, and especially autonomous vehicles, self-driving cars, and autonomous drones, autonomous weapon systems with military application. Lots of ethical questions there. In Lesson 14, we'll talk about technological unemployment, the impact that artificial intelligence has on our jobs, on the future of employment. These are both challenging ethical issues. But this lesson, for Lesson 12, I really just want to introduce the topic of artificial intelligence and talk a little bit about the history and some of the conceptual grounding for the discussions that we're going to have over the next few weeks. So this is it's a long video, but a light reading list, and the quizzes for the next few weeks is a bit different, so check Moodle for the details. I'm just going to go ahead and jump right into the topic. Hope you enjoy. Alright, so our lesson theme this week is what is artificial intelligence, and I'm going to break this down into 4 parts for this video. I want to spend most of the time talking about the history of artificial intelligence, some key points along the way of the history, and I really want to clear up one very popular misconception about AI. After the history lesson, I want to talk more directly about the philosophical issue about whether machines can think, or whether computers can think. And I'll talk here mostly about Turing's test. When that's over, I'll talk about machine learning as it exists in modern artificial neural networks. So we'll talk about deep learning. We'll talk about some of the machine learning techniques that have become very popular over the last few years. We're in a new boom in AI, the second golden age of AI, and understanding how these machines work is really important to understanding the next wave of technology. And finally, I'll raise some ethical issues about AI. I'll just sort of gesture at them right now, and we'll go into these in more detail over the next couple of weeks. And that'll be the lesson plan for today. There's 2 primary readings I want you to do for this week. One is Turing's classic 1950 article where he introduces the Turing test. This is Computing Machinery and Intelligence. I also have this other reading by my friend Peter Asaro, who in 2006 writes an article, What Should We Want from a Robot Ethic, that just raises some general issues about ethics in robotics. Apart from these required readings, I have lots of other resources in this slideshow, lots of links that you can click on to explore some of these issues more. And like I said, the quizzes this week are going to be a little bit different from previous weeks. Check Moodle for the details there. Alright, let's go ahead and jump into the history lesson. So I want to start this history lesson by trying to counteract a very popular myth. And this myth is something about the inevitability of artificial intelligence, that machines will eventually become smarter than people. It's just a matter of time. Sometimes this is put in terms of a threat, that it's just a matter of time before super intelligent machines take over the world or enslave humanity, some Terminator-like scenario. But the myth is really grounded in this idea that intelligent machines are inevitable, that computers are just getting more and more powerful, and eventually it'll eclipse human intelligence. Now, there's a source for this myth, and it's Moore's Law. Moore's Law is an industrial principle that was followed for several decades in the 20th century. So Moore was an engineer at Intel. Intel, for most of Intel, makes computer chips, processors, and so on. For most of the 20th century, the processors were increasing in speed at an exponential rate, and Moore he wasn't the first person to notice this, but he wrote this down at Intel, and it became part of Intel's planning for production planning for the rest of the 20th century. Intel worked on this what they call the tick-tock cycle, where the idea is that if the processors are going to be improving, more suggested that they were doubling their more was suggesting that they were doubling the number of transistors on a chip every 18 months. So this is exponential growth. And if computers would continue to grow at this exponential rate, then we can plan. Intel thought that they could plan around the production cycle or the marketing cycle for their chips around this rate of growth. And the cycle was called tick-tock. So the tick was supposed to be an increase, an improvement in the architecture on a chip. And then the tock was supposed to be an optimization of that architecture. And then you tick again to a new architecture, and then you optimize it, tick-tock. And the idea is to do these tick-tocks every 2 years or so. And Intel thought it could do this indefinitely. And so the idea was that if chips kept increasing at this exponential rate, then eventually they will pass human brain power. You estimate human brain power somewhere up in this region, and human brain power isn't getting much faster. Maybe IQs are increasing slightly over time. It really has a lot to do with education and testing, but your brain anatomically, neurophysiologically, is the same brain that your ancestors had 80,000 years ago, 100,000 years ago. Not much anatomically has changed about human brains over that time. Our technology has changed a lot. Our social structures have changed a lot. But our brains have not changed very much over that time. So human brains are fixed at some point on this line. Even if it's very far out from where the computers are now, the idea is that if computers keep doubling in speed, eventually they'll cross wherever it is that humans are on this line. And in fact, not just the power of a human brain, they'll cross the sum total of all human brains and keep going past that as well. Right? If computers are reliably doubling their speed every 18 months, then eventually they'll eclipse all of humanity. And so this is a point called the technological singularity. Singularity is exactly that point where the power of the machine passes human performance. And the worry is that if the machines pass human performance, then those machines will build the next generation of machines, and those even faster machines will build the next generation of machines. Soon, the power of these machines will exceed the grasp of humanity, and in particular exceed our capacity to control the machines. So these super intelligent machines will eventually overpower human beings, and maybe enslave us or do some other way pose a threat to human beings. So it was more or less true during the 20th century that computers doubled in processing speed every 2 years or so. It wasn't always the number of transistors on a chip, but it was also sort of the efficiency in which they were doing the computing and so on, was increasing at a pretty steady clip for most of the 20th century. But there's reasons to be skeptical about the singularity thesis. For one thing, more transistors doesn't mean more intelligence. Just because you can pack more transistors on a chip doesn't mean that chip is doing anything significantly more intelligent. It could just be computing, digits of pi, which isn't doing anything all that intelligent, right? So there's not just a simple correlation between transistors and intelligence. The structure of those transistors matter. What they're computing matters. So the organization of the chips, right? It's not just how fast it's computing, but it's what particular computations it's doing. And this is true both in computers and in brains. Right? Brains aren't just computing arbitrary things. They're computing very specific things that are relevant to the organism's life and well-being. So understanding not just the speed of computing, but what exactly is being computed and how that structure is organized in the brain or in a computer, right? These things matter. Another reason to be skeptical of singularity is just this idea that there's some inevitable Armageddon around the corner. It warrants suspicion. There's good reasons to be skeptical of this kind of thinking. Maybe this is also a good reason to be skeptical of the climate change discussion from a few weeks ago. Although when you look more closely at the details of climate change, suspicion, any skepticism you have should go away. It's very clear from the data that climate change is a real and serious threat. But singularity thesis doesn't have the same evidence base. In particular, Moore's law is slowing down, so it's not the case anymore that you can double the number of transistors on a chip every 18 months. For the last 10 years or so, computing power in our processors have been more or less stagnant. The speed of a desktop computer today, in terms of the CPU, is not a whole lot different from what it was 5 years ago. It's maybe a little bit faster than it was 10 years ago, but not significantly faster. There's a couple of reasons for this. One is that you can only make transistors so small before you start running into quantum mechanical interference. The point of these transistors is to send a smooth, clean, reliable signal through the chip. And if you're interfering at the quantum level, if you're getting interference, then that sort of ruins the accuracy of the computing. So you can only make these transistors so small, and that means you can only fit so many on a chip. There are ways that people are trying to experiment getting around this, 3D chips, different kinds of electrical circuits, different from the transistors, like the memristor. But these are all experimental, and they haven't proven themselves to be able to continue Moore's anticipated trajectory. Over the last 10 years, a lot of the computing research has gone into things like energy efficiency, mobility, right? Getting computers to work in your cell phone in your pocket, right, with battery life that lasts for a day. Right? These are difficult engineering challenges. Cell phones are definitely impressive pieces of machinery, but they're not exponentially faster in the same sort of way that Moore's law would have predicted from machines 20 years ago. Right? My cell phone in my pocket is about as fast as my laptop 10 years ago, but my desktop on my desk is not that much faster than my desktop 5 or 10 years ago. Some things have improved. GPU speeds have improved a lot, but these aren't core Moore's law computing benchmarks, right? So Moore's law just doesn't stand up to the scrutiny, and that means the singularity thesis sort of comes off rather weak. But the best argument against the singularity thesis is that technological change is not inevitable. Technological change it's not a force of nature that exists independent of human activity. Instead, technological change depends directly on human activity. It depends on the social, political, economic circumstances that characterize the human communities as that technology develops. And when those human communities change for whatever reason, for social, political reasons, for climate reasons, economic reasons, whatever, then that has an impact on technological change. Right? The idea of the singularity thesis in Moore's law is that the technology will change independent of anything that we do, and this just isn't true. This is sort of related to a discussion we had at the very beginning of class about technological neutrality. Remember the NRA slogan that guns don't kill people, people kill people? Right? The idea is that it's the people that are doing things, and technology doesn't do anything on its own. Right? So technology doesn't progress independent of the human circumstances, the circumstances in human communities that allow that progression. And AI gives us a beautiful example of this. For about 40 years, most people don't know this, but there was a period of about 40 years where nothing really happened in AI. This was called the AI winter. So there was an early boom in AI, and then the boom didn't really go as planned. There was a lot of hype that was unfulfilled. And for about 40 years after this hype went away, there was this period of stagnation where there was very little progress made. And this happened in the 20th century, and we saw it happen, a period of stagnation. The fact of AI stagnation, the fact of an AI winter, is of existence proof that this change isn't inevitable, that when funding dries up, so too does progress in fundamental research. Right, and funding availability is contingent on social, political, economic circumstances. So I want to sort of give you a overview of the history to combat this idea of the singularity, especially to undermine some of the hype that you might be reading about AI in the news. So here's my proposed history of AI. I break it down into 5 eras. The first is the early history of computing from the ancient world all the way until about 1950, when Turing establishes his first machines, and then they start being produced on the market in around 1950. And once computers are mass-produced and widely used in the early 50s, you get what we might think of as the first golden age of AI. A lot of low-hanging fruit. The computers are just being developed in the first place, but there's also this interest in making these computers do things characteristic of thinking or intelligence. You can actually date the start of the first golden age to a conference at Dartmouth in 1956. And this first golden age goes for about 20 years until the mid-70s, when a lot of the skepticism starts to grow, the funding dries up, and the AI winter sets in. And this goes from about 1974, from the Lighthill report. I'll go over this in a little bit more detail in a second. But from 1974 to about the 1990s. Now, in some histories of AI, there's a recognition that there's a sort of mini boom in the late 80s and early 90s. There's a few theoretical advances and a couple of major public events with AI in the late 80s and early 90s that start to spark interest again. And so there's a sort of second boom, and then there's a second winter. So there's another period of stagnation after these early theoretical successes. So sometimes you see AI Winter 1 and AI Winter 2. I'm doing it here where there's a first winter, and then there's a period of quiet progress for another 20 years. But the point is that from about the 70s to about 2012, a period of about 40 years, where not much was happening in AI, where progress just stagnated. Like I said, we're now currently in a second golden age. Second golden age of AI starts around 2012 with Greg Hinton's solution to ImageNet, and we'll talk about that in a second. But so let's go ahead and go through this history. Briefly, if you've taken computer science classes, you've probably seen a lot of this before, but we've been building machines to help us compute since the ancient world. Maybe an ancient computing machine that you're familiar with is the abacus. You can calculate numbers, addition, subtraction, multiplication, division, using these little beads. If you know how to do it correctly, you could use an abacus faster than a modern digital calculator. My grandmother could multiply numbers faster than a calculator using an abacus. And humans have been using these kinds of tools since the ancient world. So the abacus is a kind of computer. It allows you to compute functions, right? It allows you to perform a computation. It only allows you to perform these mathematical computations, and it's maybe a little difficult to learn to use, but it's a very simple kind of computer. Notice that there's no electronics in it. It's not using binary code. There's no programming involved except just moving the beads around. Right, but this is a kind of computer. Similarly, something like an astrolabe. You use the astrolabe to identify where the stars are, to figure out where the morning star will rise, and so on. You can use the astrolabe to circumnavigate the globe. Early explorers used this kind of tool in order to use the stars to figure out where they are and navigate the oceans. This is another kind of it's a calculator. It calculates the position of the stars. It computes them. This is an early kind of computer. Again, very simple moving parts. No binary code. No programming language or anything like that. It's a very simple computer. The Antikythera mechanism from around 200 BC is very complicated. device similar to an astrolabe, allowing you to calculate various astronomical events. Very complicated device from the ancient world. Maybe the culmination of these kinds of devices is in the early 1600s, the pocket watch. The pocket watch was like the cell phone of the day. It was the extremely high-tech, very expensive device that everyone had to have and carry around with them all the time. When pocket watches first came out, only the very rich people had them, but they were so useful and so important to organizing society that people very quickly figured out ways of making relatively cheap ones and mass distributing them so that very quickly everyone had a pocket watch. Pocket watches are really important for time discipline. You can't organize a society that keeps a rigorous schedule without everyone having a timekeeping device that is fairly reliable, right? If you want a train to leave at clock precisely, then you have to be able to expect that people will be there at 9 o'clock. And if people don't have watches on them, then it's not really possible to coordinate that kind of thing. Right? Before people had watches, maybe there was a town clock, and you had to be within distance of that town clock to know the time. But those town clocks weren't synchronized to anything in particular, or otherwise, you're using the motion of the sun, right? Sunrise, noon, and sunset, and otherwise, who knows what time it is? But once you have these pocket watches, you can have rigorous time discipline, and it completely restructures society. The pocket watch is a computer. It's a timekeeping device that's calculating the current time, and it's all these very sophisticated mechanisms for keeping this time precise and accurate. It's a special purpose computer. It's not a general purpose computer. But it's a thing that computes. It's a machine that computes. One more precursor to the modern computer is the Jacquard loom. Jacquard loom, it's a weaving instrument designed to make fabrics of various sorts, and in particular to put patterns on the fabrics. So weaving, this is an old hand weaving machine where you're moving the things back and forth in order to weave the fabric. But in order to get this pattern, you could do it by hand, which is long and tedious. And Jacquard in the early 1800s designed this machine with these little cards, and the cards had holes in them, and the holes allowed specific needles to fall through. And when those needles fall through, it produces a certain pattern on the fabric, right? And so creating a set of cards with specific holes punched in them, and then moving those cards through the loom as you're weaving the fabric allowed you to put a regular and precise pattern on the fabric over and over again. So Jacquard loom was a huge success in the early 1800s, and this is the framework for punch cards that came 150 years later in computers. Part of the point here was that the technologies for building modern computers, they were all in the culture, right? The technologies, the pieces required to build modern computers were all there. We just didn't do it because no one put it together in the right sort of way to see what the possibilities were. And again, this is to reinforce this point that the pace of technological change isn't inevitable, right? It's possible that someone could have figured out that this same system could be used as general computing. Someone could have figured this out 100 years before they did. In fact, someone did figure this out 100 years before they did. There's a guy named Charles Babbage. In Babbage's time, there were no automatic computers. A computer was a job that a person had. So here's a want ad from 1892 in the New York Times. Computer wanted, 1892. For a salary of between $1,000 and $1,400, you have to take a test to get the job. The test includes subjects of algebra, geometry, trigonometry, and astronomy. So $1,400 in 1892 is about $35,000 today, maybe $30,000 today. It's a low-wage job, maybe slightly more than minimum wage, but this is not a high-paid, high-skilled job. A computer was a low-skill low-wage job. The computer's job was to do mathematics, really. Before there were calculators, before there were automatic computers, if any company or any organization had a bunch of numbers that it needed to compute, add and subtract, to balance a budget or whatever, all those numbers had to be computed by hand, and you would hire someone to do this. The characteristic of a computer that you would hire is that they didn't need to know what the numbers meant. Right? If they're balancing your books, they didn't need to know whether you're making good purchases or whether you should, shift some money from one area to another. Right? Those are business decisions that required an understanding of what the numbers meant, right? What they implied for the job. The computer didn't need to know that. The computer just needed to be able to add and subtract. Right? They just needed to be able to perform the routine calculation. And this is what it meant to be a computer. A computer was someone who could perform these calculations without any insight into their meaning. And you would hire someone, a fairly low wage, to do this kind of job. But people are expensive, even for low wage jobs like this. They're expensive. You have to feed them. They can complain about things. So as long as we've been needing to add these numbers together, we've been looking for ways of automating it, right? This is what all these historical computers are really about, are ways of automating calculations. And in the early 1800s, this guy named Charles Babbage had an idea of making a general-purpose calculator, a general-purpose computer that can add, subtract, multiply, divide, arbitrary numbers that you give it. He designed this thing, he called it the difference engine in the early 1800s. I'll show you an example of a working difference engine. Oops. I guess it's not going to play in the thing. Okay. Yeah, so here's the difference engine. You can see it's a hand-cranked. It's all gears. You set an input slots, and then you turn the crank, and the gears turn around, and they're turning around this big machine. So all of these little gears and latches turn around and engage several hundred little mechanisms that allowed the whole system to add and subtract, multiply and divide, and so on as you turn the crank. Very complicated, very highly engineered, highly designed device. Babbage designed this in the early 1800s. He never actually built the thing. He built a piece of it, like a seventh of the overall design. If you know anything about computer science, each one of these columns is an adder, and Babbage built a piece of one of these columns, and he took that piece and he shopped it around to people to try to get them to help fund the full scale machine. Babbage was in England. He was especially lobbying members of Parliament to try to get funds, government funds, to build and test this device. And no one wanted to do it. Babbage couldn't find investors. Why would you invest a lot of money into an untested, unproven, very expensive machine when you can hire a person to do the same job for close to minimum wage? Right? It's a cheap job to hire someone for. Why would we invest money in this machine? So Babbage never got his machine made. He had the designs all built out. He made a piece of it in the 50s. They took his designs and they tried to build it, which is what you see here. They built it with the machining technology of the time, and it would have worked. It would have worked. We would have had a general-purpose computer about 100 years before we really did. Before we had any electricity, before we had anything like the modern digital computers, we could have had hand-cranked general-purpose computers back in the early 1800s. But we didn't, because no one understood why these machines would be useful, because no one could sort of see what Babbage was anticipating. So this is one of these examples where AI growth isn't inevitable, right? You might think that people always want the best most intelligent mechanism. Well, here it was, and no one knew what to do with it. No one knew enough to fund it, and so it sort of sat there stagnant for 100 years. And a very good example of how AI growth is not inevitable. It doesn't progress indefinitely into the future. So I said no one recognized the importance of Babbage's machine, and that's not entirely true. The one person who did was Ada Lovelace. Ada Lovelace is often credited as being the first computer programmer, and this is because of her interactions with Babbage. So Babbage was this inventor. He invented all these, not just the analytical engine, he invented all sorts of weird things. But he was also a socialite, an aristocrat. He would hold sort of fancy parties and invite people over to try to show off his machines. So one of these parties, Babbage invites Ada Lovelace. Ada Lovelace is the only legitimate daughter of Lord Byron, if you know from poetry. Lord Byron had lots of kids, but she was the only one who took his name and his title, so she was Lady Lovelace, Countess of Lovelace. Byron died shortly after she was born. Her mother also died shortly after she was born, so she was basically a titled young aristocrat with no parents and could do whatever she wanted. And what she wanted to do was mathematics. She was very interested in schooling, and she was especially had talents for mathematics. And because she had a lot of money and really nothing else to do, she was able to go to a lot of the best mathematics tutors in England at the time. And she had an exceptional skill at mathematics. It wasn't proper for ladies at the time to study mathematics exclusively, so she wasn't allowed to only study mathematics. But she definitely took an interest in it and studied it closely. And she gets invited to one of Babbage's parties in the early 1800s. And Babbage is showing this thing around. No one really cares what Babbage is doing, but then Lovelace sees the machine. Ada sees the machine, and she gets it immediately. It clicks for her. She understands immediately what Babbage is doing. She understands what the machine would do if you built the whole thing. And Lovelace is completely captivated. Her and Babbage end up forming a friendship where they correspond by letter several times. Babbage explains more about how the machine works, and Lovelace describes certain ways that you can configure the machine to calculate certain formulas that she knows from her studies in mathematics. So in these letters, in describing ways of configuring the machine, Lovelace is credited with being the world's first computer programmer, programming for a machine that wasn't even built yet. Lovelace didn't just describe how to configure the machine to solve mathematical equations. She was also imagining things like associating different numbers with notes in a musical score, and then turning the crank on the machine and having it generate new musical compositions. Right. So she's thinking about algorithmically generated music. She's very, very much ahead of her time. These images here come from a graphic novel that imagines Lovelace and Babbage's first meeting. Babbage is several decades older than her, and it's not a romantic relationship. It's a intellectual relationship, and the graphic novel imagines that Lovelace and Babbage end up becoming crime fighters and using the difference engine to solve mysteries, which is kind of fun. The reason I'm focusing on Lovelace now is because Lovelace, in these letters to Babbage, Lovelace makes one of the most important objections to artificial intelligence. This is Lovelace's objection, which is that the machine can only do whatever we know how to order it to perform. In other words, that the machine can only do what we program it to do. Most people who object to artificial intelligence give some variation of Lovelace's objection. And this is an objection that Lovelace was thinking about 150 years before we even had our first computers. So I'll come back to this in a little bit. Again, the point of all this was that Babbage could have had computers 150 years before we did. We actually had to wait until this guy, Alan Turing, who is a mathematician in the 1930s. He derives a very important mathematical result. He proves that the halting problem is undecidable. I'm not going to go into the mathematical details here, but the important point is that Turing comes to this conclusion, gives this mathematical proof by use of a mathematical formalism which has come to be called a Turing machine, or which he calls a universal computer. So here's a Turing machine. Here's a sort of simple Turing machine. I'll say a little bit more about how Turing's machines work when I talk about whether computers can think. But Turing, in the 30s, defines this machine, and it's important that it's a machine in the sense that you can build a physical device that does this thing, right? And it's before Turing comes around. Babbage proposed a physical device, but no one was ever convinced that Babbage could do it. And Turing here proposes a mathematical formalism, but he calls it a machine because he describes something that you could actually build. And then if you build the machine, it can do these certain calculations to prove Turing's result, his important mathematical result. So here's the actual building of such a machine. The machine has 3 parts. It has this tape where you can write ones and zeros in each of the cells. Then you have this head that sits over the tape. It can move back and forth along the tape to read different cells. It can write. It can read what's in the cell. It can write to the cell and change what's in the cell, and then it can move back and forth. And then so there's the tape, there's the head, and then there's the program or the control unit. And the program tells the head how to move along the tape given the inputs that it's reading from the tape. So the program, you program just this machine to move the head around the tape. If you can do that, then you can build a Turing machine. Here's what a Turing machine looks like in practice. The important part of a Turing machine is that it can perform any computation, especially a universal Turing machine can compute any computable function. Turing's mathematical result showing that a Turing machine can perform any computation allows us to define computation in terms of what a Turing machine can do. So remember, it used to be that computers were whatever human beings can do without understanding what the numbers meant. But after Turing, computation becomes whatever a Turing can do. And he gives a very formal definition, a mathematical definition of what a Turing machine can do. Once you have this kind of thing, you can start building real-world versions of it. Here's a physical device exactly modeled on Turing's machine. But the first practical applications of Turing's insights came during World War II, right? So he proves his result in the mid-30s, in the late 30s and early 40s. There's World War II, and everyone, including Turing, gets taken up by the war effort. In particular, so Turing's British, and England has a blockade around it with the German submarines, and they're bombing the hell out of London. England's in a lot of trouble, so they have this big cryptographic station out in Bletchley Park, and they asked Turing to come and see if he can help out with the cryptographic effort. In particular, what they want to do is crack the Enigma machine. This is the German Enigma machine. It was the strongest cryptographic device of its day. You could type message into this keypad, and then when you set these wheels on various settings, I think there's 20-something settings per wheel, and there's 3 of these wheels, and then you can also set this plug board up front to plug in different slots, and that also scrambles the code. Every morning, the German units would get the new encryption scheme for the wheels at the top and the pegboard in the front, and that would change on a daily basis. Once you had those codes, you could put it in and then type your message on the keypad here, and then this keypad up top would glow the encrypted letter, and then any machine set to that same configuration would be able to encrypt and decrypt their messages. But if you didn't know that configuration, there were some trillions of different possibilities that it could be in, and so it was almost impossible to figure out how to decrypt this machine. The Enigma machine is considered uncrackable, and it was this machine that was allowing the Germans to communicate with their submarines and keep the blockade up. So Turing has just figured out how to build a general-purpose computer. So him, Turing works for the British to build this machine. It's the Bomba machine. A Bomba machine is a special-purpose computer designed specifically to crack the Enigma code. They actually have a working version of the Bomba machine up at Bletchley Park, which is now a museum to computing. And the docents there, they don't have the original Bomba machine, but they built a replica of the machine, and it works. And they said they were able to intercept a German encrypted message by an Enigma machine. They were able to intercept it via radio, and then run it over to the Bomba machine and decrypt that message in about 2 hours. And these are docents, retired senior citizens who are working on the machine for fun. Military cryptographers probably be able to do it faster than that. So it's a very impressive machine. Able to decrypt the Enigma device is no joke. So Turing essentially uses his general-purpose computers to help the war effort defeat the Nazis. Turing is also gay, and that's a criminal offense in England at the time. After the war effort, Turing's a hero, but he's not allowed to say anything because he's working for this top-secret program. Turing, at one point, he's out dating people like a normal human being, but he's gay, so he's dating men, which is illegal at the time. He happens to date a man who is in with like a rough crowd and decides to rob Turing. Turing's boyfriend and this other dude break into Turing's house and steal a bunch of stuff. Turing gets, understandably upset, calls the police. The police come over and ask, why is there another man in Turing's house? Instead of going after the criminals, they arrest Turing. They convict him of indecency in 1952. The punishment for indecency in England at the time is chemical castration, where they feed you hormones designed to make you not gay anymore. They feed you testosterone, designed to make you not gay anymore. Of course, that doesn't work. Feeding you hormones like that really just changes your body metabolism. Turing gained a lot of weight. He became very depressed. In 1954, he was found dead of cyanide poisoning in his home. A lot of people think that Turing committed suicide deliberately out of depression from his treatment. Some people think that maybe he didn't commit suicide deliberately. Maybe it was just an accident. Turing was doing a lot of chemistry experiments in his home at the time, working with cyanide. He also had a habit of eating an apple at the end of the day, and so it's possible that just he was careless in his experiments and his apple became laced and he ended up dying from poisoning that way. But either way, he was sentenced to he was tortured for being gay. This is what we do to our geniuses. He wasn't officially pardoned until 2014. If you're interested, here's Benedict Cumberbatch, who plays Alan Turing in the Imitation Game movie from a few years ago. I'm reading a letter from Turing from immediately after he was arrested. I'm going to skip that here, just for sake of time. So Turing dies in 1954. He's arrested in 1952. One of the very last things he does with his time in the 1950s is talk about artificial intelligence. So remember, before Turing, computers was a job that humans had. So early computers, like for instance UNIVAC in the 1950s, they didn't call them computers. They called them computing systems, but there was no real term for what you call these big machines. And the public was a little bit worried about them. In 1951, UNIVAC helped tabulate for the U.S. government, helped tabulate the United States Census. Every 10 years we do a census. In the 1950s we do a census, and UNIVAC was processing a lot of the results from that census. This exposed the public to one of the very first computers that was commercially available. UNIVAC also did a presidential prediction for the 1954 election. I believe Eisenhower won, but most people were predicting that Eisenhower would lose, but UNIVAC predicted that Eisenhower would win, and so this got UNIVAC a lot of public attention also. But the public didn't really know what to think about these systems, didn't really know how to treat them, and because of science fiction at the time, people sort of got a little bit concerned. Are these machines a threat? Might they hurt us? The popular press didn't call them computers because that was a job that humans had. Instead, they called them thinking machines or mechanical brains. And when you call something like this a mechanical brain, it's going to get the press both excited and concerned. Is going to stoke a lot of public fears. So Turing thought that he had some obligation to talk to the public about what these machines are, what they can do, and to address the question, can machines think? And in 1950, he writes this article, Computing Machinery and Intelligence, which is one of the required readings for this week, where he addresses this question explicitly, can machines think? And in this article, he proposes his solution to this question, which has come to be called the Turing test. And I'll talk about this in a bit. Let me just finish up the history really quickly. So once computers are out and about in the early 50s, Dartmouth has this conference, very famous conference. This is where the term artificial intelligence is coined. All of the early AI people, Minsky, Herbert Simon, Newell, Shannon, all the big early AI computing people are at this conference. And the point of the conference is to discuss whether every aspect of learning or any other feature of intelligence can be so precisely described that a machine can be made to simulate it. Basically, these are people who are really excited about the new computers and what they might be able to do, and in particular that they might be able to do things like thinking, like what we do when we think. So this early conference brought together a bunch of people talking about artificial intelligence. Shortly after this conference is over, there's all these sort of breakthroughs in early artificial intelligence. ELIZA in 1964 is a therapy bot, it's a chat bot. You can talk to it in English. Here's a little transcript of an ELIZA conversation. And you can say things to it, and it'll ask you questions about what you said. ELIZA isn't really that, especially if you've talked to any chatbot today. ELIZA looks pretty simple. Basically, all ELIZA could do was take what you say and turn it into a question and ask that question back to you. This is actually a style of therapy. It's called Rogerian therapy, question therapy. But the point of Rogerian therapy is that you don't actually say anything to the patient except just repeating what they say, and then sort of posing that as a question and trying to prompt them to say more things. Right, so this is a style of therapy. ELIZA was mimicking Rogerian therapy, basically just by repeating a question with maybe some grammatical changes, and then asking that question back to the respondent. But people would talk to ELIZA for hours at a time. Deep into the night, they would have these cathartic therapy sessions with ELIZA. Even the grad students who built ELIZA would feel like they had really worked something out with ELIZA. Another early success of the first golden age of AI is Shirtaloo. This is Terry Winograd. So Shirtaloo is a general-purpose reasoner. Again, using natural language, you can tell Shirtaloo to perform a task in this little block world. So it couldn't do anything in the real world, but there's this little block world that has blocks and pyramids and boxes, and the pyramids can go inside the boxes or can stack up on top of the boxes. You can do different things to this world, like pick up things and move them from one place to another. And Shirtaloo understood how this world worked, and understood the kinds of things, the commands you gave it, and would follow them. Right. So if you told it to pick up the red block, it would pick up the red block. If you told it to put the red block on the pyramid, it would say, I can't do that, because it knows that you can't put a block on a pyramid. You can only put a pyramid on a block. If you put the block in the pyramid, then the block will fall over, and so it just won't let you do that. So Shirtaloo understands how the world works, understands the implications of instructions that you give, right? Like that you can't pick up you can't pick up this block because there's a pyramid on top, so you have to pick up the pyramid first. These kinds of things, and it understood this all in natural language. People would claim that Shirtaloo was a general intelligence, or general purpose reasoner, general intelligence. Not general intelligence in the real world, general intelligence in this little toy world, but it was still a general kind of intelligence. You could use natural language to talk about it, and it understood what you were saying. Maybe the biggest early success in AI was the perceptron in 1957. Perceptron was designed to model a learning machine very much like neural networks. The idea was that neural networks, you have a bunch of nodes in the network, and they all hook up in a particular way. So the perceptron is designed to model the same thing. So you have a bunch of input nodes, and all of these nodes are connected by a single function with a weight. So this input times this weight, plus this input times this weight, plus this input times this weight, and so on and so on and so on for all the different inputs that you have. You take each of those inputs, you multiply them by their specific weights, and those together, and that gives you the perceptron output. The perceptron is supposed to be a learning machine, and it learns by adjusting these weights, right? So you have some input, you have a function, adding those inputs together when you multiply them by the weights. And so you can change this overall function by adjusting the weights, changing the weights slightly. And if you change the weights slightly, that means that the overall function that you get is going to be slightly different. So for example, say you want to classify a data set. Say you have a set of cats and dogs, and you have them, you know their sizes, and you know how domesticated they are. And imagine you can quantify how domesticated they are. And so you have a data set with a bunch of animals of different sizes and different levels of domestication. And the perceptron wants to learn to classify these. In other words, to draw a line in the data set so that all the cats are on one side and all the dogs are on the other. Right? If you only have 2 points, it's pretty easy to draw that line. The more data you get, the more you have to adjust this line so that all the dogs are on one side and all the cats are on the other. But the perceptron could do this, and the perceptron could learn classification schemes that successfully get the dogs on one side and the cats on another. If, and this is the big trick, if you can only do this if the data set was linearly classifiable. In other words, that the data could be completely cleanly divided with a straight line, as you see here. If the data was nonlinear at all, in other words, if it wasn't possible to do the classification with just a straight line, then the perceptron couldn't learn that task. In the early 50s, we built a perceptron trying to get it to learn. And then in the late 50s, we realized, no, okay, there's this fundamental limit on what the perceptron can learn. It can't learn nonlinear data. And since most of the data in nature is nonlinear, this was a fundamental limit on what the perceptron can do. And this made a lot of people worried. So on the one hand, you had these Dartmouth people who were hyping up the near future of AI. Herbert Simon in 1965 says, a machine will be capable within 20 years of doing any work a man can do. Simon says this in 1965. In 1985, it definitely wasn't the case that a machine was able to do the work of any man. In 1970, Marvin Minsky in Life magazine says, in from 3 to 8 years, we'll have a machine with the general intelligence of an average human being. He said in 1970, it was not the case in 1978 that we will have a machine with the general intelligence of an average human being. Right, by the 70s, it was clear that this kind of hype, these kinds of radical predictions, were just not going to come true. And especially once these mathematical limitations on the perceptron were understood, a lot of this hype looked shallow, and people stopped believing it. And very quickly, the field of artificial intelligence and anyone who said anything like this became a laughingstock. And this brought about the end of the first golden age and the beginning of AI winter, maybe signaled most clearly by this conference paper that Drew McDermott gives, where he criticizes AI for all of this unnecessary hype and for all these bad programming techniques and so on. And he says, as a field, artificial intelligence has always been on the border of respectability and is therefore on the border of crackpottery. Many critics urge that we're over the border, and a lot of people started saying that anyone who's saying that these machines are thinking, they're just crackpots. In the early 70s, the Lighthill report comes out. This is a British report sort of summarizing a lot of the hype and the unfulfilled promises of AI. And it was after the Lighthill report that the British government stopped funding AI. And shortly thereafter, DARPA, the United States funding agency, also cut all its funding to AI. In addition to this, in the mid-60s, Herbert Dreyfus It gives a report about what machines can't do, and in particular talks about the limitations of this sequential kind of programming that characterized these early computers. This is the period of AI winter where funding dries up. Anyone working on AI is called a crackpot, and most of the activity is really in the criticisms of AI from Dreyfus, from Searle in the 1980s, who gives the Chinese room argument. Maybe we'll talk a little bit about that in a minute. But again, this is 40 years where AI just doesn't do very much at all. Right? You have this early boom in the 50s and 60s with ELIZA and Shirley perceptron, and then it all just stops, comes crashing to a halt, and winter sets in. Winter starts to thaw in the late 80s when the mathematical limitations in the perceptron are overcome. A few people, they call themselves the connectionists, like Rumelhart, figure out that you can build a perceptron that learns nonlinear data if you add what are called hidden layers. So here's the input layer, here's the output layer. The perceptron just took the inputs, added them all together with their weights, and put them in the outputs. But if you add additional layers in between inputs and outputs, and that's all it means, layer is just that they're in between the inputs and the outputs, then you can prove mathematically that a network with hidden layers can learn not just nonlinear data, but is in fact Turing complete and can compute any computable function or any function that's computable by a Turing machine. So you can build a neural network with at least one hidden layer. You can build that network to learn any possible computable function. So if you can compute it with any kind of machine, you can compute it with one of these neural networks. So this mathematical discovery happens in the late 80s. This starts to attract more attention to the field of neural networks, but it's still kind of a niche field. There's still a big stigma against it. Only a few people working. A lot of the really early advancements were not in AI generally, but in things like robotics. For instance, Rodney Brooks in the late 80s and early 90s starts talking about what he calls the subsumption architecture, which is about how to move a robot around in the world. This is partly influenced by things like Dreyfus's criticisms of what computers can't do. So in the early 2000s, iRobot puts out Roomba, which goes around cleaning floors. The thing about the Roomba is that it's not particularly intelligent. It doesn't have a map of the space. It doesn't have very strong sensors, so it can't figure out where it's going. The Roomba basically just moves forward until it bumps into something, and then turns around and moves in a different direction until it bumps into something else, and it just keeps moving in these random directions. Eventually, it'll clean the entire floor, but not because it's particularly intelligent, but because it knows how to move around in the world. Right, so these are the kinds of progress that was being made in the early 80s and 90s and early 2000s. Another really big advance that was important technologically, really with robotics, is the Grand Challenge. In 2004 was the first Grand Challenge. Grand Challenge was supposed to see if you can get self-driving cars to drive through the desert. In 2004, there was a 100-mile track, and none of the cars that entered made it more than a few hundred yards from the starting point. Most of them failed very, very soon after the starting point. In 2005, they have a redo of the match, and some of the big robotics departments in the big research schools, like Carnegie, these big research universities enter in to the race. Their cars in 2005, a few of the cars actually finished the race, and almost everyone who works on this race at the time ends up being bought up by the big tech companies and are responsible for a lot of the self-driving car innovations today. So a lot of this happened from the DARPA Grand Challenge back in 2005. DARPA, I should mention, is the Defense Advanced Research Projects Agency. The Defense Advanced Research Projects Agency. This is the research and development wing of the United States military. DARPA used to be just ARPA, like the ARPANET, the Advanced Research Projects Agency. ARPA built the internet back in the 60s and 70s. And over the last maybe 20 years or so, DARPA has been investing heavily in robotics technology. So the reason we have self-driving cars is partly because of heavy investment from the military over the last 20 years or so. One other maybe big thing that happens in the Quiet Progress era is the Kasparov versus Deep Blue match. This is an exhibition match. It's really a marketing stunt by IBM. IBM builds this special purpose chess playing program in the 90s called Deep Blue. This is right in the middle of the AI winter. The connections are really just starting to get going, and AI is still pretty much a joke. So when IBM does this, it's really just a marketing stunt to try to attract attention to their hardware, and it's not really a lot of progress in fundamental AI research. But still, the goal of building a chess-playing program has been around since Turing. Turing himself designed programs to play chess. They weren't very good, but even back in the 50s, Turing is thinking about chess-playing programs, and Turing's also thinking about chess as a way of evaluating the intelligence of machines. But there was never very good computers for a long time. In 1996, IBM built a machine called Deep Thought, and Deep Thought could compute 1 million moves a second. Deep Thought plays Kasparov. Kasparov beats Deep Thought pretty easily. And then IBM comes back in 1997 with Deep Blue. Deep Blue is special purpose hardware that can compute 1 billion moves a second, much faster than Deep Thought. And Kasparov plays this exhibition match against Deep Blue in May 11th, 1997. And if you're looking for a date when computers took over the world, it was May 11th, 1997, at this exact match between Kasparov and Deep Blue. And this is actually worth going into some detail about. Kasparov was probably the greatest chess player to have ever lived. He was the best chess player at the time, for sure. Maybe there are people who are better than him today, but Kasparov was considered by many the best chess player to have ever lived. Kasparov could beat every other chess player. He was the highest ranked chess player. He couldn't just beat every other chess player. He could beat three. So they rank grandmaster. They rank chess players. You're a novice and you're a master, and the highest rank you can have is grandmaster. And they would say of Kasparov, there were the grandmasters, and then there was Kasparov in a league of his own. Kasparov could beat any other grandmaster. He could beat 3 grandmasters at the same time. He would set up 3 chessboards right next to each other, 3 different grandmasters on the other end of those chessboards, and he would play 1 move per game against all 3 at the same time and beat all 3. He would beat 3 grandmasters in this way while blindfolded. He was a phenomenal chess player. No one in the world could beat him. In fact, in the early 90s, before Kasparov played Deep Blue, there was a website you could go to. It was Kasparov versus the World, and everyone in the world. It was an early website. You could go and vote on what the next move would be in a World versus Kasparov chess match. And Kasparov kicked the world's ass. It wasn't even close. In a democratic voting system like that, the results tend to be the safe, predictable move, right? The average move voted by everyone is going to tend to be fairly safe and predictable, and Kasparov knew exactly what to do with safe, predictable moves and destroyed humanity, right? Kasparov could beat every person on the planet at chess, both individually and collectively. And maybe it's worth mentioning here that chess is the game of kings, right? Chess is the game of strategic, rational thinking of the sorts that only human beings can do. And in fact, we've often pointed to chess and the kind of strategic, tactical thinking required in chess as an example of human rationality, as an example of the kind of capacity for human thought that exists in no other animal, right? I mean, a horse is never going to play chess. My cat is never going to play chess, or even understand the basic, what the game is about, right? The kind of abstract thought required for chess is characteristic of the very thing that makes us human. So chess is the sort of pinnacle of human rational thought, and Garry Kasparov is our best example of a chess player, right? So this is humanity's peak, shining pinnacle, and this is exactly why this is where computers take over the world, because IBM builds this special purpose machine to play chess. And before we go into the details of the games, let me say a little bit about chess. If you don't know chess, here's the starting position on the chessboard. There are 16 pieces on each side. It's 8 by 8 square. You have a bunch of pawns, 8 pawns, and then all these special purpose pieces. So white goes first. White can move any of the pawns, either 1 square or 2 squares. So 8 pawns, so 16 moves. Or white can move the horse here or here, and move this horse here or here. So it's 16, 17, 18, 19, 20. So for the first move, white has 20 possible moves to make. And black has 20 possible responses. Black can move either of its pawns and its horses. In the first round, black and white can't interact yet. So we can imagine drawing this as a big graph, right? So the starting state of the board is just this state in the starting position, and then from the starting position, white has 20 possible moves, and then for each one of these starting positions, black has another 20 possible moves. And then you can imagine sort of drawing, so right, for each one of these squares, each one of these red squares, black has 20 possible responses. So that's 20 times 20. So just for white and then black responding, there's 400 possible moves. And you can imagine for each move there's another 20 possible moves. In fact, the game actually, once the pawns move out, the game opens up and you get a lot more than 20 possible moves. Like, for instance, a bishop might end up being able to move in one of several different squares, or a king or whatever. So after the game opens up, you get more than 20 moves for every move before it. But you can imagine, on average, about 20 moves per move before it. The average game of chess lasts about 35 moves. So imagine 35 sets of this over and over. But 35 moves is the average game of chess. Chess can go on significantly longer than that. So for a rough estimate of how big, right? So imagine drawing out this full pyramid, this full search tree for chess. How big would it be? Or how many different nodes would it be? Or you might ask, if you draw out this full chess game in complete detail, how many nodes would be at the bottom? This is, in other words, asking how big is it required to solve chess? Because you can't play the perfect game of chess unless you have this full tree written out, right? So how big would this game be? Well, so Claude Shannon estimates, this is a conservative number, or it's a generous number. This is probably too big, but Claude Shannon estimates that there are about 10 to the 120 possible games of chess. In other words, if you fill out this whole tree, there would be about 10 to the 120 nodes at the bottom. So 10 to the 120 different paths through this tree to get to the nodes at the bottom. 10 to the 120 is a huge number. For reference, there are about 10 to the 80 particles in the universe, 10 to the 80 protons in the universe. 10 to the 120 is significantly bigger than 10 to the 80, which means that there are far more chess games than there are particles in the universe, which means that if we were to assign one chess game to every particle in the universe, we'd run out of particles before we run out of chess games. The search space for chess is huge. It's beyond astronomical. And what that means is that it's impossible to play a perfect game of chess. In order to play a perfect game of chess, you'd have to have this whole tree filled out, and you have to know exactly how to move through this tree in order to do the best possible move at each step. And you can't do that for chess. You can do that for other games. Actually, let me get out of here. They have what are called solved games. Solved games are games where the entire play is known, that they've played through every possible game, and we know exactly what the strongest move is at every step. Right. So we have solved games that we know perfect play for. For instance, checkers. Checkers or English draughts. drafts. Checkers is weakly solved. We played through almost every game of checkers. There's some sort of endless variations that we haven't played all the way through, but we solved all the important variations. We've played through every game of checkers, and that means we know how to play the perfect game of checkers. You can program a computer to always make the best move in a given checkers position. Since we've played through every game of checkers, we know that checkers is fair. We know that red and black have an equal chance of winning. There's something possible games of checkers. It took 18 years to calculate every single possible game of checkers, but we've played through all of them. We started in the 80s, and we did most of it in the last few years, up to 2007. But now that we've played through every single game of checkers, we can play the perfect game of checkers. Tic-tac-toe is solved. If you are over 6 years old, you should never lose a game of checkers. A game of tic-tac-toe. Tic-tac-toe is solved. You should always be able to play a perfect game of tic-tac-toe, and a perfect game means that you should draw every game of tic-tac-toe. If you lose a game of tic-tac-toe, something has gone dramatically wrong. Anyone over 6 years old should be able to play tic-tac-toe. Because the tree isn't that big, it's very obvious which moves are required to win the game, which moves are certain death. So here's XKCD gives the complete perfect play for tic-tac-toe. If X goes in the top left corner and O goes in the top middle, then X can go in the center, and then you can sort of play through all the variations here. This isn't every single possible variation, but this is given these starting points. Here's all the different play for X and for O. This tells you who wins, who draws in every one of these scenarios. So you can play the perfect game of tic-tac-toe. You should never lose a game of tic-tac-toe. In order to play a perfect game, you have to have solved these trees. And let me remind you again that chess, in order to solve the chess tree, you have to have 10 to the 120 possible games of chess that you look at, which is more than there are particles in the universe, which is just something that's physically impossible for a computer to do. It's not possible for a computer to play through every possible game of chess. There are too many games. And what that means is for Deep Blue to play chess, Deep Blue has to make some decisions. It's got to make some hard decisions to evaluate which moves deserve being looked at more closely and which moves can be safely ignored. Right. So we said that there are 20 possible white moves at the start of chess. So there's 20 possible moves, but like some of these moves, like moving the pawn up 2 spaces as your first move, that's not a very good move. The good moves control the center pieces, so that's really moving some of these center pieces or maybe the horses on the inside. Moving the horses to the outside is also just not a good move, right? So some of these moves just aren't good. So you might think that of these 20, maybe these 8 moves in the center, and the ones over here aren't so good and we can ignore those, and ones over here aren't so good and we can ignore those, but these 8 in the center are worth looking at more closely and looking at the next level down. And maybe at this next level, these 5 are the good moves and the rest of them we can ignore, and then you go down a few levels. So this is how Deep Blue has to make its choices. It has to evaluate which of these chess positions are worth deeper analysis and which of these chess positions can be ignored. And there's no exact way of doing this correctly because you can't play the perfect game of chess. So Deep Blue has to make choices. It has to go through calculations to run evaluations to see which of these moves are any good. Deep Blue's ability to make these choices is trained from looking at lots of old games, from being tweaked by the designers and engineers of Deep Blue. But Deep Blue could make, like I said, a billion calculations a second. It's looking at a billion different chess moves every second and evaluating their relative positions to see which is the best move. So like I said, IBM built Deep Thought, I think, in 1995. IBM builds Deep Blue in 96. Deep Blue does a billion moves a second. Kasparov plays Deep Blue in 1996. In the first 1996 match, Kasparov wins 4-2. Deep Blue takes a couple of matches off Kasparov, but over the course of a 7-game tournament, Kasparov wins 4 games against Deep Blue's 2. and that's enough to win the tournament. At the end of the first 1996 match, Kasparov has a press conference where he explains that the computer's really smart. It's calculating really quickly, but it's just not processing the chessboard in the same way that the human being is. Humans are just too quick. We're too clever. The computer's just not in a position to match human performance. And Kasparov says at the end of that first match, it's probably not in our lifetime, probably not in my lifetime, will I see a computer beat the top-ranked chess player. Kasparov says this in 1986. 1987 is a rematch. Kasparov agrees to another exhibition match. It's good fun. He gets a lot of money. At the end of the first game, Kasparov wins again. It's a fairly straightforward match. Kasparov has played enough of these computers to know how to beat a computer. Really, the trick is to get the computer into a position where it's just not sure what to do, sort of a position that it probably hasn't studied very deeply before. And if you can get a computer into these kinds of positions, maybe Kasparov has a bit of an advantage. So Kasparov in this first game sort of wipes the floor with Deep Blue again, has a press conference at the end of this first game, and again says, probably not in my lifetime will I see a computer beat the chess grandmaster. And then game 2. This is the game where the computers take over the world. In game 2, Deep Blue makes a couple of very surprising moves, including a move that eventually leads the Deep Blue to sacrifice its queen. The queen is the strongest position, the strongest piece on the board. Sacrificing the queen is a big risk, but Deep Blue ends up gaining a strategic position advantage on the board as a result of this queen sacrifice, and eventually beats Kasparov. When Deep Blue plays this move, this sacrificing move, Kasparov is stunned. He's shocked. He doesn't believe it. The moves that Kasparov makes after Deep Blue makes this move are sloppy, and in fact, the analysis afterwards shows that Kasparov could have turned the second game into a draw, but Kasparov, after this move, was just so shaken that he loses game 2. Kasparov ties the next 3 games and then loses one more game in game 6 to lose the series, 3.5 to 2.5. Deep Blue beats Kasparov, the best chess player on the planet, and now the computers are in charge. Kasparov doesn't believe it at first. Kasparov thinks that a computer couldn't have made that move. The move was too clever. It was too insightful. You didn't have to be a genius. Even a normal grandmaster chess player could have looked at the board and seen this move and could have programmed Deep Blue to make it, right? So Kasparov, at the end of the second match, instead of congratulating his opponents, Kasparov demands to see the logs, says it has to have been a human. Some human intervened and made the computer make this move. The move was too clever to be made by a machine. I don't know if we've seen the logs yet. Deep Blue's in a museum somewhere, but it doesn't really matter if. So maybe the first thing to say is that Kasparov is accusing IBM of running a mechanical Turk. The mechanical Turk. So we've been playing chess for a long time, thousands of years, and it's the game of kings. Kings like to play chess, and kings like to think of themselves as great chess players. And the thing about kings is that if the kings lose, they might kill you. They might cut your head off. So kings like to play chess. Kings don't like to lose at chess. And people don't like beating kings at chess. And one of the things that this means is that sometimes kings walk around thinking that they're much better at chess than they actually are. Napoleon was a famous example of this. Napoleon thought he was wonderful at chess, and that was just because anyone who played him chess would let him win, because if you beat Napoleon at chess, he would throw a tantrum, and things would be awkward or difficult, or people would die, right? So don't beat Napoleon at chess, just let him win. But that means that Napoleon was going around thinking that he was a great chess player, when in fact he was garbage. So people didn't like this. Someone had the great idea to build this device. He called it the Mechanical Turk. And it was sort of a magic trick, right? You open up the front, there's all these gears and levers that you'd expect from like a pocket watch, but there's nothing else inside except these mechanical parts. But the machine, they say, plays chess. And you close it back up, and you turn the crank, and then it starts playing chess. In fact, what's going on is that there is a person inside, and the person has their own small chessboard that they're using to figure out the pieces and relay those moves to the operator at top, right? So the Mechanical Turk appears to be a machine, but in fact it's a human. Amazon, if you don't know, has a web service where you can solve simple problems of the sort that are difficult for machines to solve, but easy for humans to solve. And you can sign into the Mechanical Turk or mturk.com and get paid some very small fees for doing very simple menial tasks. So Amazon is sort of playing on this Mechanical Turk idea, and Kasparov accuses IBM of running a Mechanical Turk that Deep Blue couldn't have made the move that won Game 2. IBM, I don't know if IBM gave up the logs, but it doesn't really matter anymore because you can buy off-the-shelf software that'll run on your laptop that is more powerful than Deep Blue was. I don't remember the best computer playing program before Zero. Stockfish was one of the very good ones. But Stockfish can beat any Grandmaster. You put the highest performing Grandmasters. I think Magnus Carlsen is the top chess player today. And Magnus Carlsen will get beaten very easily by even a very simple laptop computer running the latest software. Because your laptop computer is several hundred times more powerful than Deep Blue was at its peak. So our best chess player gets beat by a machine in 1997. In 2011, so a little bit over a decade later, IBM has another similar kind of exhibition match. This is also in this second period of winter, this sort of quiet progress period. IBM puts up Watson in an exhibition match, this time not against chess, but against Jeopardy. Watson plays Ken Jennings, who is the longest winning streak in Jeopardy history. He won the most consecutive games. And this guy is Brad something, I forget his last name, but Brad is the highest dollar value won in the history of Jeopardy. And IBM puts Watson up against Ken Jennings, and Ken and Brad are best Jeopardy players. And if chess is difficult, I remember when Kasparov beat Deep Blue at chess. I was in high school at the time. I remember reading the papers saying, well, okay, so a computer can beat chess, but chess is this very formal, rigorous, mathematical game, exactly the sort of game that computers are well suited to. But try to get a computer to beat Jeopardy, something like Jeopardy, which requires a deep familiarity with the language. Jeopardy answers require trivia of the sort that can't easily be formalized. Trivia knowledge. It requires knowing how to work with puns and wordplay. It's very common in Jeopardy questions. And that kind of stuff is very difficult. It requires not just facts at hand, but it requires an understanding of the language. It requires some critical, clever, creative thinking. So when Watson beats the pants off its human opponents, this is a feather in the cap of artificial intelligence. These machines are beating our best human performers at tasks where we would human being intelligent if they beat these tasks. Right? Everyone thinks that Kasparov is a really bright guy. You might call him a genius. Kasparov doesn't know everything, but Kasparov is definitely a example of extreme intelligence in chess. Similarly, Ken and Brad here are examples of extreme intelligence in Jeopardy. They don't know everything. There's lots of things they don't know. But if you ask the average person, are these intelligent people, they're going to say yes. Right? These are examples of what we would consider an intelligent person. Right? Not that they're perfect by any measure, but that they're examples of human intelligence. Maybe high-end examples of human intelligence. Both Deep Blue and Watson are expert systems. Expert systems means that they're sort of specially designed to do one kind of task very well. Deep Blue was designed only to play chess. It really couldn't do anything else. Watson IBM wants to market Watson as a sort of general purpose intelligent framework, but Watson is really a special purpose database management system that allows it to retrieve answers in natural language very quickly. And it's really this database management that makes Watson capable of doing the kinds of tasks it's able to do. But these expert systems really aren't characteristic of the progress in AI over the last, since the 90s, during this quiet progress period. Did I pass it already? So in the early 80s, there was this advancement with neural networks, and people were still tinkering on them for a while. And in the late 90s, Yann LeCun, who for a while was the director of Facebook research, but in the late 90s, Yann LeCun came up with this idea for convolutional neural networks. Explain maybe a little more in detail later, but so in the 80s, they overcame the problem with the perceptron. In the late 90s, they started optimizing these networks to be able to do some heavy-duty computation. And in 2012, and this is really where the recent boom in AI starts. Geoff Hinton, who is a Canadian AI researcher who had been working on these neural networks since the 90s, he takes Yann LeCun's convolutional networks and builds a system that solves ImageNet. So ImageNet is this. It was a standard image challenge for AI in the early 2000s. It was just a database of a bunch of pictures, and then the pictures were classified as what's in the picture. So this is a mite, this is a container ship, and so on. And the task was, can you take that data set of pictures and correctly identify what's in the images? For years, this was an unsolved problem, and this is why people just didn't take AI seriously. But in 2012, Hinton uses these convolutional networks to solve this task, and people start taking note. In 2007, a few years before this, Hinton gave a talk at Google. Google has these talks where they invite academics and authors and whatever to give a talk. Hinton goes and shows Google his neural networks in 2007. A few years later, Hinton beats ImageNet, and then in 2013, so in 2012, Hinton solves ImageNet using these convolutional networks. In 2013, just the next year, Google hires Hinton to head up their AI research program, and Hinton uses his neural networks and applies them on products almost immediately. In particular, starts using them on mobile applications. So by 2014, your text-to-speech app in Google Hangouts is being run by a neural network, taking the speech that you say and turning it into text, and it's using Google's using a neural network to do this. So Hinton getting hired by Google. This is where I mark the recent boom in AI starting. And the important thing about this is that Hinton isn't just doing fundamental research. Hinton is showing the tech industry how to turn these research tools into marketable products. So this is why the second golden age of AI that we're in right now is different from the first golden age. The first golden age, there was progress, but there was never any marketable products. Right? There was never any results that found their way into consumer hands. And this changes in the modern boom. You have almost immediately applications of these neural networks to mobile consumer products. And this sets off the boom. Google pours a bunch of money into AI, and so does all the other big tech companies. Amazon, Microsoft for a while, Facebook. Facebook hires Yann LeCun, the guy who develops the convolutional networks originally. Google also hires Boston Dynamics, the big robotics company, in 2014. Amazon hires a bunch of people. Apple has been behind in AI for a while and is just starting to catch up recently. Uber hired a bunch of people. IBM, of course, has Watson. And there's just huge investment in this time period, artificial neural networks. Elon Musk also donates or invests a ton of money into AI. Musk also in 2015 donates about $10 million to the Future of Life Institute to study existential risks posed by artificial intelligence, how much AI threatens human safety. And it's this $10 million donation from Musk that really launches a lot of the popular concerns over existential risk and threats from AI. And then, sort of cap it off, just recently, in 2016, AlphaGo beats Lee Sedol. So I remember when Kasparov loses to Deep Blue, people would say that, so it's impressive that the computer beats chess, but chess is this sort of formal game that's very suited to what computers can do. And even still, a computer's never going to beat a human being at Go. I mean, chess is really a complicated game, 10 to the 120 possible games of chess. But Go is orders of magnitude larger. I think there's something like 10 to the 170 possible games of Go. Just to, I don't have a image of the Go board here. Go looks like this. If you don't know Go, it's black and white pieces on this big board. The pieces go at the intersections. They don't go inside the square, but they go at the intersections of the squares. And the goal of the game, it's not to capture any particular piece, like capture the king. The goal of the game is just to take up as much space on the board as you can. Whoever occupies more space, more territory on the board, wins. And you don't have to capture pieces to get this, but you can capture pieces. The way that you capture pieces is by completely surrounding them. So you see these two. So this white piece right here, there's one black piece on one line from that center. If black were to put pieces on the other three lines from that center, then that white piece would be completely surrounded, and black could take that piece off. Right, so that's called a capture. These intersections are called liberties, and the single white piece has 4 liberties. If black can put pieces on all 4 liberties, black can capture that piece. And the way that you avoid capture is by putting another piece next to you, and then pieces that are touching of the same color share their liberties. So in order to capture these 2 pieces, you have to put black pieces here, 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 and here. So there's 6 spots that you'd have to put in order to capture just those 2 pieces. So you can protect your pieces by extending liberties, right? So in order to capture this, you have to surround that whole segment and so on. This is how Go works. It's pretty easy to play, but the possibilities are astronomical. So the Go board starts with a completely empty board, and you can put a piece anywhere on the board you like. The board has 19 by 19 spaces. It's about 20 by 20. So white has 20 by 20, about 400 options for where to put white's. Black goes first. So black has about 400 options for where to put black's first piece, and then white has 400 minus 1 options for where to put their next piece. So that's 400 times 400. 400 squared possible moves in just the first white-black response. Remember, it was 400 possible moves in chess. It was 400 possible moves, 20 possible moves for white, and then 20 possible responses for black. It means 400 possible moves in the first white-black round. In Go, it's 400 possible moves for just white, and then 400 possible responses for black. So it's 400 squared moves for just the first round of Go. And Go tends to last much longer than chess. The games go longer. There's more moves in the game. So this is a significantly more complicated game than Go. And I remember during Deep Blue's defeat of Kasparov, people saying, well, not in our lifetime would a machine get beaten at Go, or would our best Go players be beaten by a machine. And almost 20 years to the day, Kasparov was beaten May 11th, 1997. AlphaGo was beat the world's best Go player in May 26, 2017. It's almost exactly 20 years to the day. The top ranked Go player is not Lee Sedol, but is a Chinese player named Qi Jia. Qi Jia is the top ranked Go player, but because he's Chinese, there's political complications with having an American tech company beat the top-ranked Chinese player. So in 2016, AlphaGo beat Lee Sedol. Lee Sedol is, I think, the 6th highest Go player, highest ranked Go player. So he's an extremely good Go player, but he's from South Korea, so there's not the same kind of political difficulties. AlphaGo beat Lee Sedol in 2016 in a best of 5 match. AlphaGo took 4 games off Lee Sedol, and Lee Sedol took 1 game off of AlphaGo. And then AlphaGo comes back in 2017 and beats Kijia in an exhibition match in a best of 3. AlphaGo wins all 3 of those games. Not only does AlphaGo win all 3 of those games, but there's another match with 5 9 Dan. In Go, you have a rank sort of like in Black Belt Dan. The first master is a 1 Dan, and you go 2, 3, 4, 5. The highest ranked master is a 9 Dan. And they during this exhibition match, they had 5 9 Dan Go masters who had been preparing all week for this game against AlphaGo. And they were playing together, so they were all coordinating on this board. And this was the leader, and he was playing on the board against AlphaGo. And AlphaGo beat all 5 of those players at the same time. So it was AlphaGo beating a 45 Dan opponent, they said. I guess I want to show this one little clip from game 2 in the Lee Sedol match. So here's the actual match in the corner. These guys are commentators talking about the game. You can see there's time ticking down. You have 2 hours per play. And the person here, the commentator, is explaining why the pieces in this area aren't very strong for black, so there's really no reason for black to play a piece in this area. But you can see that black AlphaGo just played a piece right here.
Thore from the Google team was talking about is this kind of evaluation value?
That's a very surprising move.
I thought it was a mistake.
Well, I thought it was a click miss, but
a clicko. And if we were online Go, we'd call it a clicko.
Yeah, it's a very strange. Something like this would be a more normal move.
Okay, actually, you're going to have to. So, do you have to think about this?
This would be a kind of a normal move, and white would answer here. But actually, since this group is so strong, maybe white wouldn't.
Okay. Right, that's right. Because what you were just saying, that's just settled. Right.
Because even if black does stuff like that, even after playing all its moves, it's still strong.
It doesn't change it, right?
Doesn't change. Well, these stones might get a little weak, but the value of this is relatively small. So we don't really know if white would answer this or not. White's going to answer this. This is almost as close as an attachment move. It's diagonal, so it's a bit further away, but like if black continues with this, it would be very effective.
Interesting. So AlphaGo played this move, which I want to hear more about in a second, but Lee has left the room.
He left the room after that move.
He left the room after that move.
Uh-huh.
I'm not even going to ask.
He had to go and wash his face or something just to recover from it. It's a very surprising move.
It's a surprising move.
I wasn't expecting that. I don't really know if it's a good or bad move at this point.
All right, I'm going to pause it there. So, just as we saw with the Deep Blue Kasparov match, where Deep Blue plays a move that completely floors Kasparov, and he doesn't expect it. It's not the kind of move that Kasparov was expecting, so it throws him off the rest of the game. So this is exactly what you're seeing here, the same kind of thing. Commentators talking about how it doesn't make any sense to play this move. AlphaGo plays exactly that move. You can see the commentator, I think he does a quintuple take. He does a 5 take. He looks back and looks again. It's pretty hilarious. Not expecting that move would get played. And if you watch the clip again, the commentator is shocked at first, and then as he reasons it out, he realizes, in fact, this is actually a really strong move, and AlphaGo is in a much better position for making this move. This is sort of the rule with artificial intelligence, right? We underestimate their potential, how clever of moves they're capable of making, and then they end up making moves that just completely floor us, shock us. It shocks Lee Sedol so much that he has to stop playing, and he actually gets up out of his chair and leaves the room. You can see here at the very end, he's not. This is the person making moves for AlphaGo, and Lee Sedol has just left. While his time is counting down, he only has 2 hours, and the move sends him out of his chair into the other room. Yeah, so that's AI for you nowadays. AlphaGo is also not an expert system in the same way that Deep Blue was. Right? Deep Blue was designed specifically to solve chess programs. Watson was a special purpose database that could solve Jeopardy programs. But AlphaGo uses a technique called Monte Carlo tree search. So remember, part of the problem with chess is that the tree is so big that it's difficult to move in the tree. So what AlphaGo does is a special method for deciding which moves to look, which moves not to look at. This is called Monte Carlo search. Monte Carlo is a method for generating random moves, and the idea is that it can take a statistical sample of random moves and then use that sample to decide where the best moves are. So it's a very smart way of pruning the big search tree into a more manageable shape in order to find moves quickly. AlphaGo required training from millions and millions of human-played games in order to get this good, and lots of special tweaking. After AlphaGo beats the best players in the world, DeepMind, who built up Google, AlphaGo is built by DeepMind. DeepMind is the research branch of Google, or the sort of research-focused branch of Google. So after AlphaGo beats all the best Go players, DeepMind tweaks AlphaGo into AlphaGo Zero. And the thing about AlphaGo Zero is that it doesn't use any human play in order to achieve its high performance. Instead, it just engages in self-play. So whereas the original AlphaGo was taught by millions of actual human play games, AlphaGo Zero only plays itself. When it first starts out playing itself, it's really bad. But as it continues to play itself, it improves over time. It gets better and better and better until eventually it passes first the original version of AlphaGo, and then the top-ranked version of AlphaGo. So AlphaGo Zero reaches top-rank mastery in just a few days, in just a few hours. It does this after millions of games of self-play, so it takes something like 50 million games for AlphaGo Zero to reach the best player in the world at Go. Something like 50 million games. The average human Go player plays about 50,000 games before they reach top mastery level, 9-dan status. Your average 9-dan plays about 50,000 games. AlphaGo Zero is playing about 50 million games to reach the same level of player, to beat that level of play. So AlphaGo Zero is still requiring far more games in order to hit that level of mastery, but it can do it very quickly. It can go through those games so quickly that it can, within just a few days, become the best player in the world. 40 days, a little over a month. And to prove the flexibility of this, DeepMind then took AlphaGo Zero and generalized it so that it could play just about any game. AlphaGo Zero was the Go playing program. AlphaZero is a general program that can play just about any game you give it. So they gave it not just Go, but they gave it Shogi, which is another kind of game, and then they gave it chess. The best open source chess playing program at the time was Stockfish, and AlphaZero engaged in a bunch of self-play until it played at the same level of Stockfish. DeepMind released a few games between AlphaZero and Stockfish. Stockfish, again, was one of the better chess-playing programs at the time, and AlphaZero just wiped the floor with Stockfish. Some of the games are embarrassing for Stockfish, and it's very impressive that AlphaZero, using the same kind of quick tree search, ends up becoming the best chess player, not just the best chess player in the world, the best Go player in the world, the best shogi player in the world, and the best Atari player in the world. Basically, any game that you give AlphaZero, it can, but through only self-play, very quickly achieve world-class performance. And this is shocking, right? It's shocking partly because these are not expert systems. These are not hand-tuned top-down systems, but these are really the machine learning for itself. Just to end this bit of a history lesson and move on to the next section, here's a survey that was done last year interviewing artificial intelligence experts, asking them when they think important milestones will be reached by AI over the next few years. So when will machines be comparable to human performance at Angry Birds, at World Poker, at StarCraft? So we already have a machine. When this survey was published, between the time that the survey was sent out and the time it was published, we'd already built a machine that can beat World Series of Poker professional players. So we've already beaten there. The next major game to fall will be StarCraft. There's a lot of money, a lot of investment, a lot of research going into building a machine that plays convincing StarCraft at better than human levels. We have some really good human players. We don't have computers that can beat human players yet, but that'll happen very soon. Generate a top 40 song, drive a truck. Most experts are estimating this is in the 10 to 15 year range. Out here at the 10 to 15 year range is also playing Go with the same training set as humans. So we already have computers that can beat us at Go, but can they beat us at Go by only looking at 50,000 games, the same as a human master? In the long term, do things like writing a best-selling novel, being a surgeon, engaging in AI research, full automation of all labor. They're guessing 125 years. This big line is the error bars. So people are very uncertain about what's going to happen in the future of AI. And I think it's probably unwise to be predicting more than a few years out for AI. But that's, I think, the end of my history lesson. And I'm actually, because this video has gone on for several hours, I'm going to end the history lesson now. And I'm going to do a new video for part 2 where I talk about can computers think. So I have a lot more to say. I'm only about halfway through with my slideshow, but I'm going to go ahead and end things there and pick up in a second video, part 2, Can Computers Think? All right, thank you very much.